In the picturesque town of Gatlinburg, Tennessee in November of 1956, a gathering of brilliant minds in the nuclear physics field convened for the Conference on Neutron Physics Topics. Physicists worldwide presented their data on nuclear resonance's energy spectrum, but the limited and imprecise experimental data led to significant doubt about the distribution of energy spacing. Despite this, the prevailing wisdom was that the distribution should be a Poisson form. Among the distinguished attendees was the renowned mathematical physicist Eugene Wigner. As the audience eagerly awaited his insights, Wigner knew he had to put forth his best ideas. With great poise and confidence, Wigner took the stage, adjusting his glasses as he faced the expectant crowd. "Perhaps I am now too courageous," he said with a hint of humor, "when I try to guess the distribution of the distances between successive energy levels of heavy nuclei." He then surmised that the correct distribution should be of this form rather than the Poisson distribution. At the time of the Gatlinburg Conference, no more than 20 S-wave neutron resonances had been resolved. Therefore, it was impossible to make a definitive test of the Wigner surmise. Immediately following the conference, experimental physicists from all over the world gathered all their data to obtain the first global spacing distribution of S-wave neutron resonances. Remarkably, their combined results showed a perfect agreement with the Wigner surmise. To make predictions in physics, you usually need to know the Hamiltonian of the system. Wigner was able to guess the energy spectrum distribution despite not having the Hamiltonian of a uranium atom or even having much experimental data. This remarkable story of the fusion between physics and math is the topic of this video. Wigner went on to win the Nobel Prize, introduce group theory and symmetries in physics, and write a widely acclaimed essay on the unreasonable effectiveness of mathematics in physics. The video is divided into two parts. In part 1, we review Wigner's essay and go through his arguments to understand precisely what he meant when he used the phrase unreasonable effectiveness. In part 2, we'll present our partial solution to the question. We believe that universality is a vital piece of the puzzle in explaining why mathematics is so incredibly effective in science. If you find part 1 not so math-heavy, don't worry. In part 2, we do have a mathematical treat for you. We will thoroughly derive Wigner's surmise and try to motivate why it is so interesting. Part 1. Wigner's tale begins with two friends, one of them a brilliant statistician working on a population distribution. When the statistician started explaining the symbol pi in a Gaussian distribution, his friend couldn't hold back and burst out with a hilarious response: "Surely the population has nothing to do with the circumference of a circle." Wigner learns a lesson or two from this story. He notes that the mathematical concept comes up in entirely unexpected connections. This enormous use of mathematics in natural sciences is something bordering on mysterious, and so far, no rational explanation exists. Much of what Wigner argues depends on what he means by mathematics. Wigner doesn't say much about the definition of mathematics, but what he says is suggestive. Wigner writes, "Mathematics is the science of skillful operations with concepts and rules invented for this purpose. The principal emphasis is on the invention of concepts." Here we should note that Wigner, like many scientists, blissfully ignores some of the seminal contributions from philosophy to the understanding of mathematics. His view of mathematics, emphasizing the importance of rules and the human creative element in creating concepts and rules, contradicts some dominant views on mathematics. The world around us is filled with baffling complexity, and it is very hard to predict the future. However, despite this complexity, certain regulations can still be discovered. One such regularity was discovered by Galileo, who discovered that the two rocks dropped at the same time from the same height and reached the ground simultaneously. Physics is concerned with such regularities. These regularities are surprising for multiple reasons. The first is that it is true not only in Pisa and Galileo's time, it is true everywhere on the Earth, was always true, and will always be true. This regularity is called the invariance property. The second surprising feature of this regularity is that it is independent of many conditions that could affect it. It is valid whether it rains or not, whether the experiment is carried out in a room or from the Leaning Tower, no matter whether the person who drops the rocks is a man or a woman. Historians trace the origin of the modern sensibility of mathematization to Galileo onwards, and he is attributed to the quote that the laws of nature are written in the language of mathematics. Wigner argues that this role of mathematics and physics is now more accurate than ever before. For this, he points out that the modern mathematical formulation of quantum mechanics requires using complex numbers. The space where the quantum state lives is a complex Hilbert space endowed with a Hermitian scalar product. Surely, to the unpreoccupied mind, complex numbers are far from natural or simple, and physical observations cannot suggest them because we only observe real numbers in experiments. Here, we would like to take the opportunity to present some new results that have come in the last few years. In a paper published in Nature in December 2021, physicists claim that quantum theory based on real numbers can be experimentally falsified. The idea goes like this. Naively, one might think that the complex numbers in quantum mechanics are mostly fake. They can be replaced everywhere by real numbers with the expense of having two wave functions to encode the real and imaginary parts. However, this new paper proved that real and complex Hilbert space formulations of quantum theory make different predictions in experiments. Two different experimental groups immediately verified their proposal, proving that quantum physics indeed requires complex numbers. Wigner then argues that the success of mathematics in physical theory is truly surprising because in many cases, we got something out of the equation that we put in. And these mathematical concepts are not natural or straightforward in any common sense way. He finally concludes his essay in a cheerful note. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift that we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and will extend to wide branches of learning. Part 2. In Part 2, we will try to answer some of Wigner's questions and occasionally challenge him. Wigner claimed that the enormous usefulness of mathematics in the natural sciences has no rational explanation. Well, we believe we do have a partial answer to his question, which pertains to the concept of universality. Nevertheless, before diving into that, let's look if mathematics is really effective at explaining natural sciences. Starting off, we have classical mechanics, a world of remarkable regularity. Think of the elegant equations that succinctly describe the orbit of a planet. Newton's laws encapsulate this simplicity beautifully. Next up, quantum mechanics enters the scene, introducing a touch of stochasticity and increased complexity. Yet the Schrödinger equation manages to capture this in a surprisingly concise manner. Interestingly, if you introduce lots of randomness, you enter the world of statistical mechanics and thermodynamics. Despite the chaos, these systems can be elegantly encapsulated with compact mathematical expressions. In these two limits, one where things are highly regular and the other where there is pure randomness, mathematics is exceptionally effective at explaining it. This also explains why physics is so successful at these limits. But here's where it gets truly intriguing. In the center, where randomness and regularity compete for dominance, mathematics turns out to be not so effective at explaining it. One example of such a domain is biology and chemistry. We don't yet have a mathematical equation fully explaining a biological cell. It might be true that some new mathematics might be required for this. Wigner was particularly concerned about the case with high regularity. He was posing a profound philosophical question on the nature of physical laws, and mathematics being the language of it. For that, we don't have the answer. However, as we venture to the opposite end, where randomness rules, we stumble upon a fascinating insight. When things become astonishingly intricate, a paradox emerges. Complexity becomes simplicity. That is, when things get too complicated, it starts to become easy. This is where universality comes into play, shedding light on the interplay between chaos and order. We refer to universality as a phenomenon where seemingly different complex systems show similar patterns. This brings us to the field of random matrix theory, a field pioneered by none other than Wigner himself. So what is a random matrix? Well, it's just a matrix whose elements are random variables. No big deal. So why all the fuss about it? Because they're extremely useful. Just think about how many random variables are helpful. If someone throws 1,000 fair coins, you can make a somewhat confident prediction that the number of tails will not be too far from 500. Okay, maybe this is not really that useful, but it shows that sometimes it is far more efficient to forego detailed analysis of individual situations and turn to statistical descriptions. This is what random matrix theory is about, but instead of replacing deterministic numbers with random numbers, it replaces deterministic matrices with random matrices. Anytime you need a matrix that is too complicated to study, you can try replacing it with a random matrix and calculate averages and other statistical properties. Matrices are everywhere in physics and mathematics. They appear as soon as there are linear relations between variables. Randomness is also everywhere, so it is only natural that random matrices should arise in many places. Hearing about random variables and probability, you might think of giving up the video. Instead, let's refresh some basic probability theory essential for understanding the content of this video. Probability theory. First, a random variable x is neither random nor a variable. Whatever it is, it can take values in a discrete alphabet or on an interval of a real line. For the continuous case, p of x is the probability density function of x. The probability that x takes values in the interval a to b is given by this expression. A die will not blow up and disintegrate in the air. One of the 6 numbers will eventually come up, so the sum of probabilities of the outcomes should be 1. People call this property normalization. If we have 2 random variables, x1 and x2, they must be described by a joint probability density function. This quality gives the probability that the first variable, x1, is in the interval a to b, and the other, x2, is simultaneously in the interval c to d. Joint probability can be considered the probability of 2 events happening together. For example, the probability that a card is a 5 and black is 2 by 52. When the joint probability density functions are factorized, i.e., it is the product of 2 density functions, the variables are said to be independent, otherwise they are dependent. When in addition we have this equality criterion, random variables are called IID, independent and identically distributed. One popular probability density function that we will also frequently refer to is the Gaussian or normal probability density function given by this expression. The parameter mu is the mean of the distribution, and sigma squared is its variance. Random matrix theory is a happy marriage between linear algebra and probability theory. The main essence of random matrix theory can be formulated in very simple terms. We are given matrix X of size n by n such that the matrix entries have some joint probability density function. The goal is to say something about the eigenvalues of the matrix X. Here is an example of a 6 by 6 matrix X whose entries are independently sampled from a Gaussian probability density function with mean 0 and variance 1. Some entries are positive, some are negative, and none is very far from 0. There is no symmetry in the matrix at this stage. Recall that a real symmetric matrix has n real eigenvalues. To get real eigenvalues, the first thing to do is to thus symmetrize our matrix. Following a common symmetrization trick, the symmetric matrix looks like this, whose 8 eigenvalues are now all real. Congratulations! You've produced your first random matrix drawn from the so-called Gaussian orthogonal ensemble. Wigner's surmise random matrix theory. The most straightforward, yet very instructive, complete analytical calculation we can do is for 2x2 random matrices. Wigner did this calculation to predict the nuclear spectrum distribution. For now, we will treat it as a pure mathematical problem, which goes as follows. We are given 2x2 real and symmetric random matrix with x1 and x2 picked from a Gaussian distribution with mean 0 and variance 1, while x3 is picked from Gaussian distribution with a mean 0 and variance 1/2. Suppose lambda 1 and lambda 2 are two eigenvalues of this random matrix. The question is, what is the probability density function of the difference between these two eigenvalues? The two eigenvalues are random variables, as matrix elements are random variables. Thus, S is also a random variable. So the first thing we can do is compute the characteristic equation and its eigenvalues. This gives us the expression for the following eigenvalues and the spacing. By definition, the probability density function for the spacing distribution is then given by the integral. The job of the delta function is to enforce the definition of S. If we can perform this integration, we have the answer. To do this integral, we can notice that there is a sum of two squares, so the natural thing to do is go in polar coordinates. The right change of variable is this. Next, we know we must compute Jacobian and express integrand in the polar form. Once we do that, we get the expression for the spacing distribution as follows. Psi goes from minus infinity to plus infinity as x1 and x2 goes from minus infinity to plus infinity. The delta function can significantly help us by killing one of the integrals. We can change every occurrence of r with s. The only thing to be careful of is that r goes from 0 to infinity, so s cannot take the negative value. The theta integral gives us 2 pi, and we can bring the term involving s outside, leaving a normal Gaussian integral for pi. From this, we get this very simple result for the probability density function of the spacing distribution. As an exercise, you can check whether this satisfies the normalization condition. This spacing distribution is also called Wigner's surmise, which we introduced at the beginning of the video. Why is it defined as a surmise? After all, it is the result of an exact calculation. Wigner did the same calculation we did for 2x2 matrix and guessed that the distribution should also be similar for the complicated system. More on the physics later, but for now, let's see it as a pure math result. Now, let us try to validate our findings through a simple MATLAB solution. Here's a code that generates 300,000 random symmetric matrices, computes eigenvalue spacing, and constructs a normalized histogram. This visual comparison helps us evaluate the correspondence between computed and anticipated eigenvalue distributions as per the Wigner surmise. Despite its simplicity, this is actually a quite deep result. It tells us that the probability of sampling two eigenvalues very close to each other is very small. It is as if each eigenvalue felt the presence of the other and tried to avoid it, but not too much. A bit like birds perching on an electric wire or parked cars on a street, not too close or far apart. Now back to Wigner. Wigner was interested in the energy spectrums of heavy nuclei such as thorium and uranium. While theoretically much more complicated than the hydrogen nucleus, these nuclei are accessible to neutron scattering experiments. The nuclei have large numbers of energy levels, which appear in experimental data as peaks of the diffusion rate of neutrons as a function of the energy. The interesting observable that Wigner wanted to study was the statistical distribution of the distance between neighboring energy levels. To understand this, we have to go slightly beyond the realm of a real symmetric matrix. Hermitian matrices are a complex variable cousin of symmetric matrices, defined as matrices equal to their conjugate transpose. Here is an example of such a matrix. The most interesting property of a Hermitian matrix is that all eigenvalues of such matrices are real. Hermitian matrices are fundamental in quantum mechanics as the eigenvalues of such matrices are what we observe in a lab. Experiments include position and momentum operators. The eigenvalues of a matrix are discrete, giving origin to the quanta nature of the position and momentum of particles. One very important such Hermitian operator is the Hamiltonian of a system. The eigenvalues of a Hamiltonian are the system's corresponding energy levels, which is precisely what Wigner wanted to study. Since the Hamiltonian of such atoms must be extremely complicated, the second best thing Wigner could do was to replace this complicated Hamiltonian by a random Hermitian matrix and study its eigenvalue statistics. Surprisingly, the eigenvalue statistics of random Hermitian matrices are very close to what we observe in the lab for uranium atoms. Application to the buses of Kathmandu. We were talking about nuclear systems, and now we're talking about the buses of Kathmandu? What on earth would they have anything in common? But surprisingly, patterns from random matrix theory emerge in seemingly unrelated phenomenon from bus systems in Mexico to chicken eyes, prime number distribution in number theory, and quantum mechanics. Here we borrow the work of two physicists from the Czech Republic, Milan Kurbalik and Peter Seba, who studied the bus system of Cuernavaca in Mexico. Suppose you arrive at a bus stop in Europe. The sign says that buses arrive every 10 minutes on average. The probability that the next bus will come in the next 5 minutes is given by a curve known as the Poisson distribution. However, the situation is completely different in Cuernavaca. Unlike other metropolitan bus systems, this system is totally decentralized, with no central authority or timetables. The bus system of Kathmandu, Nepal is also very close to that of the Cuernavaca bus system. One of the editors of this video happens to be there at the moment, so we have some actual footage of what we are describing. First, no leading companies are responsible for city transport. Thus, there are no timetables for the city buses, and sometimes not even well-defined bus stops. Moreover, the driver is usually the owner of the bus, and so he aims to maximize the income. Since every passenger entering the bus has to pay, the driver tries to collect the largest possible number of passengers. Third, there is a competition among buses. This conversely means that they tend not to arrive at a given bus stop immediately after their predecessors. To achieve that, they learn information about the departure time of the previous bus from bystanders. Adjustments are made using mental arithmetic without any advanced algorithms. Milan and Peter Seba collected a record containing 3,500 arrivals of buses during the time period of 27 days. They found that the spacings between buses agree accurately with the statistics of random matrix theory. The Gaussian unitary ensemble gives the best approximation to the uniform spacing that the bus drivers can achieve based on the limited information available to them. It is remarkable that so large a public benefit results from so simple an optimization process. Proper analysis of random matrix theory might allow Kathmandu and Cuernavaca bus drivers to do their job better. We have barely scratched the surface of random matrix theory. We have included some reference materials for you in the description. There are wide applications of random matrix theory, from quantum gravity, chaos theory, number theory, machine learning, etc. Now it's time to conclude. In the video, we have argued that one major reason mathematics seems so effective at explaining reality is because of its universality property. One good, simple model can predict phenomena of many diverse fields. At the same time, nature seems to repeatedly use a good idea. Just think of how many different ways a harmonic oscillator seems to appear. However, we have to admit that we have not answered Wigner's original question at all. His question was on the origin of the laws of physics. Here is a naive attempt to answer it. It could be that out of all possible physical laws, we can use Occam's razor-like argument, which states that the simplest object has the highest probability, to pick out some physical law in favor of others. One criteria could be that only laws that exist are of the simplest kind. We can make this idea more rigorous using the concept of Kolmogorov complexity. Kolmogorov complexity is the length of the shortest effective description of some object, so it could be that the existing physics laws have the shortest Kolmogorov complexity. Let's end this video with some modern remarks on Wigner's questions. Physicist Max Tegmark argues that mathematical existence equals physical existence, and all structures that exist mathematically exist physically as well. If they don't exist in this universe, they exist in some other multiverses. So in his argument, mathematics effectively describes the physical world because they are equivalent to it. On the other hand, highly influential mathematician Michael Atiyah turned the tables with his essay, The Unreasonable Effectiveness of Physics in Mathematics. He argued that the toolbox of physicists enables a practitioner like Edward Witten to go beyond standard mathematics and make substantial progress there.